This is a stupid meme, I'm sorry, but I couldn't think of any other ideas for the thumbnail. To be clear, I think it's good to be clear about what assumptions you're using, even if those assumptions are self-evident, whether you're doing math or anything else, really. But there's a philosophy called formalism that seems to be relatively common among mathematicians that says that mathematical statements aren't meaningful on their own. They're only meaningful relative to certain assumptions. And clearly this works for doing mathematics because proofs work no matter what your motivation is for discovering them. But as a foundational philosophy, this is completely uninteresting to me. You're just giving up on the question of truth. That's not much of a philosophy. In a lot of cases, though, it does make sense. There are all sorts of mathematical objects out there that are defined by obeying certain properties, and we can investigate what can be proved from these properties without any notion of them being absolutely true or false. Right? They're true for some things and false for others. Like Euclidean and non-Euclidean geometry, for example, have different consequences, and both of them are interesting to explore in their own way. But this idea that statements can never be absolutely true or false, only true or false relative to certain axioms, this falls apart at the most obvious example: numbers. 2 plus 3 equals 5, right? Can we all agree on that? Sure, it's not literally impossible that I'm wrong about this. There's a Descartes quote that goes, "I sometimes think that others go wrong even when they have the most perfect knowledge, so how do I know that I myself don't go wrong every time I add 2 and 3? And I think it's a good point. You know, I don't know, but I have no real reason to doubt it. And I think even the most devout formalist would be unhappy if I handed them 2 $1 bills in my left hand and 3 $1 bills in my right before running off with one of their hundreds. If it was discovered tomorrow that the standard axioms of mathematics proved 2 plus 3 equals 6, we would change the axioms. We would not change the arithmetic. We understand what it would mean to check if x plus y equals z, at least for relatively small numbers x, y, and z, and we're confident that anyone who checked correctly would get the same answer. So unless we insist on complete philosophical skepticism, there's no good reason not to regard this as a meaningful question with a definite truth value. But on the other hand, if statements can't be phrased in terms of things that could, in principle, be checked, then it seems to me that we don't have any grounds to declare them meaningful, or even definitely consistent. You know, the reason I'm confident in the consistency of arithmetic is because I can imagine what it physically means, and I'm confident that this imagination is consistent. For statements that we can't even imagine a physical meaning for, I don't see a good philosophical justification for their consistency, only an empirical one. You know, if nobody's found a contradiction yet after looking for decades, then they're probably consistent, but that's not very satisfying. I didn't come to math to rely on empirical evidence like that. So the question is, how far can we get with this idea? How much of math can we claim to be intrinsically meaningful? Ultimately, this is a little bit subjective. You have to decide what counts as a valid check, and there's a trade-off to be made between certainty and mathematical expressivity. But this trade-off should be made very carefully. Not all mathematical statements are created equal. If we think 2 plus 3 equals 5 is meaningful, that is not evidence that the continuum hypothesis is meaningful. And if we think the continuum hypothesis is not meaningful, that is not evidence that 2 plus 3 equals 5 is not meaningful. Pure formalism says that no mathematical statement is intrinsically meaningful. And pure realism says that every mathematical statement is intrinsically meaningful. I think these positions are overrepresented among mathematicians, and I suspect this is because they provide simple answers to philosophical questions that most people would rather ignore in favor of the actual math. And that's totally fair. I'm not trying to throw shade on any individual mathematicians. It's perfectly reasonable to focus on other things, although I do wish that, as a whole, this question got more attention than it does. Personally, I view these two extremes as reasonable hypotheses that, when we actually look at the math, happen not to fit the data. Okay, originally numbers were for counting physical things, right? And an ultra-finitist would say this is their only valid use, and the only valid check of x plus y equals z is to count a group of x things, count a group of y things, and then count that together they make z things. So 1 plus 1 is true, 2 plus 2 is 4 is true, but the only thing we can say about like Graham's number plus Graham's number equals 2 times Graham's number is that it can be proved from certain axioms. We only really have experience with arithmetic on small numbers, and so we're not justified in extrapolating to large numbers. and indeed we're not even justified in extrapolating the notion of number beyond values that can be physically instantiated. An ultrafinitist can do math just like anyone else, but they just have to be a formalist about almost all of it. I think there is some sense in which the ultrafinitist is right. Like, arithmetic statements that have actually been physically verified, maybe technically we should have more confidence in them than those that have not. But I also think this difference is negligible because statements about larger numbers could be verified in principle, by which I mean I can imagine someone verifying them, and I'm confident that this imagination is consistent. So to me, the benefit of being able to talk about these larger numbers is worth the very slight dip in confidence, in the same way that being able to talk about physical objects like this really existing is worth the very slight possibility of being wrong due to living in the Matrix or whatever. But this is not a logical argument against ultrafinitism, it's just a leap of faith that I personally am willing to take. I really do see no good reason for at least being an ultrafinitist if you're going to do math at all, because any proof is equivalent to a statement of arithmetic, so if you think proofs are or are not valid, you should think that arithmetic statements are or are not true. But how far beyond that you're willing to go is a question of faith, and I think any decision is understandable. What I don't understand is why so many people do math while professing not to have this faith that it actually means anything at all. To me, the beauty of math is the meaning, but never mind. Onwards and upwards. So a finitist would argue any equation relating finite numbers is meaningful. Numbers above a certain threshold may only be an idealization, but they're a clear and coherent idealization that can be meaningfully studied. We cannot imagine an actually infinite computation, but we can imagine arbitrarily long finite computations, and so they should be considered to have definite results. Similarly, any arithmetic expression involving bounded quantifiers, like for all x and y less than a googol, x plus y equals y plus x, this is meaningful because this could also, in principle, be decided by a finite computation. But what about when we remove the bounds? Is it meaningful to ask whether, for all x and y, x plus y equals y plus x? Finitism means different things to different people, but according to the strictest possible reading, no. We can only assert that a statement is meaningful if we can also assert that it can be decided by a finite computation. So if p of x is some arithmetic statement with no unbounded quantifiers that involves a free variable x, we can assert that p of a is meaningful, whatever a happens to be, but we cannot assert that for all a, p of a is meaningful. We cannot make statements about all finite numbers, because there's no such thing as all finite numbers. The finite numbers do not end. To accept the meaningfulness of statements about all finite numbers is another leap of faith, but even before we went all in on infinity in modern times, this was still relatively uncontroversial. Euclid's Elements, written over 2 millennia ago, presents an elegant proof that there are infinitely many prime numbers. This book is one of the earliest examples of what could be called formal deduction. It starts out with a list of axioms and endeavors to prove everything else from them. But was Euclid a formalist? Of course not. He was trying to understand the world around him, and he discovered a fact about the world around him, that no matter what number you pick, there will always be a prime number greater than it. And 2,000 years later, we're still stuck on a similar question. No matter what number you pick, is there always a twin prime greater than it? A prime which is 2 more or less than another prime. Imagine 2 people, Alice and Bob, playing a game. Alice selects a number, and then Bob selects a number. If Bob's number is a twin prime that's greater than Alice's number, Bob wins, otherwise Alice wins. Now nobody knows the answer to the twin prime conjecture, and so nobody knows who has a winning strategy. But whether we know about it or not, it feels intuitively clear to me that the winning strategy exists, and one or the other of them has it. Certainly both people don't, and what would it mean for nobody to have it? Again, this is a small leap of faith, but if we accept it here, we should accept it for any game that takes a finite number of turns, and where, no matter the player's decisions, the rules for deciding who wins are already understood to be meaningful. So mathematically, this includes all arithmetic statements with alternating quantifiers. Statements like, for all a1, there exists a2, such that for all a3, there exists a4, such that blah blah blah, all the way up to an, and then some arithmetic statement with no unbounded quantifiers that relates a1 through an. But why stop there? We could easily write a program to enumerate the syntactically valid statements of arithmetic, call them statement 1, statement 2, etc. And then we can ask things like, are all the prime statements true? This is a little bit of a silly question because whether a number is prime has nothing to do with what arithmetic statement it represents, but we should certainly accept it as meaningful. The justification is exactly the same, right? Alice picks a number. If it's prime and the corresponding statement is false, Alice wins, otherwise Bob wins. And no matter her decision, the question of who wins is meaningful, as we've decided, and we've already decided that if winning is meaningful, then having a winning strategy is meaningful. And the same argument works for any statement of the form, for all A1 there exists A2 such that for all A3 there exists A4 such that blah 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 all the way up to AN, and then some statement with no unbounded quantifiers that relates A1 through N using arithmetic and the predicate statement X is true. I know that's a little bit complicated. The exact details aren't super important, but as an example, for all A there exists B such that statement A times B is true. We can call statements like this statements of 2 arithmetic. And then we can enumerate the statements of 2 arithmetic and talk about statements like, for all A there exists B such that A less than B, and statement B of arithmetic is true, and statement B of 2 arithmetic is true. And we can call statements like this statements of 3 arithmetic. And then we can do 4 arithmetic and so on. We'll figure out that statements of n arithmetic are meaningful for any n, and so we can combine all of them into one single list of statements of omega arithmetic, and then we can talk about those in statements of omega plus 1 arithmetic. There's no end to this process, because whatever statements we've recognized as meaningful so far, we can always enumerate them and then make new statements about them that we also recognize as meaningful. This, as I understand it, is the philosophy of predicativity. The name comes from the fact that predicativists don't accept the existence of arbitrary sets of natural numbers, only those that can be defined using a predicate that only refers to subsets of natural numbers already understood to exist. For example, if we accept the existence of S, the set of natural numbers that refer to true arithmetic statements, then we can define T, the set of all natural numbers A, for which there exists B, such that A times B is in S. And then the statement T equals N, the set of all natural numbers, is equivalent to the statement for all A there exists B, such that statement A times B is true. But on the other hand, the set of natural numbers that refer to true statements of second-order arithmetic, that is, statements involving arbitrary natural numbers and arbitrary sets of natural numbers, well, if we don't accept the existence of arbitrary sets of natural numbers, this is clearly nonsense. The predicativist really makes very few assumptions. Basically, all natural numbers exist, and if a question is understood to be meaningful when asked of a single natural number, it is understood to be meaningful when asked of all natural numbers simultaneously. And you'd be surprised how far this can get you. An alternative line of reasoning that leads to similar conclusions is this. A computer that performs step 1 in a half second, step 2 in a quarter second, step 3 in an eighth of a second, etc. This may be physically impossible, but who says we can't imagine it? If this computer were to exist, wouldn't the result of its computation be just as definite as the result of any finite computation? Any infinite collection that can be paired with the natural numbers is called countable. So if we accept the result of countable computations as meaningful, we are countabilists. On the other hand, the subsets of natural numbers are said to be uncountable, because they cannot be paired with the naturals themselves. So just as a strict finitist would be happy to talk about any particular number that you define, but not all natural numbers, one could be a strict countablist, happy to talk about any particular subset of the natural numbers that you define, but not all subsets of the natural numbers. Personally, I'm willing to go one step farther and combine these two ideas. Right, the universe could, in principle, be countably infinite in size, and so I accept that any subset of natural numbers, whether we can define it in finite terms or not, could in principle be physically realized by a countably infinite string of zeros and ones. And, in principle, Alice and Bob could play a game where they take turns picking subsets of natural numbers, and if it's meaningful to ask who wins, I accept that it's meaningful to ask who has a winning strategy. Statements about sets of natural numbers, to me, have a satisfying philosophical justification for consistency. But beyond that, all bets are off. In ZFC, the standard axioms of set theory, When you have a set S, you're allowed to create the power set, the set of all subsets of S. So not only can you talk about sets of natural numbers, but also all sets of natural numbers. And personally, this is where I draw the line. I don't think an arbitrary subset of B is a clear idea. It's clear when B is the natural numbers because we can sort of imagine countable infinity, and a subset of the natural numbers only encodes a countable amount of information. It's just an infinite string of zeros and ones. That's not too bad. But what does an arbitrary set of sets of natural numbers look like? How would we, even in principle, specify one? Statements about sets of naturals have this weird vibe about them. Something just feels off. The continuum hypothesis, which I mentioned earlier, is the classic example. Does there exist a set of sets of natural numbers which is larger than the naturals and smaller than the full set of all sets of naturals? This statement is independent of ZFC, but so are plenty of other philosophically innocent ones like the consistency of ZFC. So that's not the problem. The problem is when you look into why it's independent, you find that set theorists have constructed models in which it's true and models in which it's false, and there's no really solid reason to believe in one over the other. The problem is people can't agree on whether the question is even well defined. The problem is that the meaning is simply not clear. What is an arbitrary set of sets of natural numbers? ZFC is the standard foundation for mathematics. And yet most mathematics can be done with a very small part of it, second-order arithmetic, statements about sets of natural numbers. And to me, this part makes sense and the rest feels like a fever dream. Set theorists, to quote Joel David Hampkins, who is among other things a set theorist, build models to order. With no clear guidance from the universe on which properties their models have to have, they can create all sorts of models with all sorts of different properties, limited only by their imaginations. They've started lucid dreaming, and that's cool, but it's not, I think, reality. Deriving the formal consequences of ZFC can be interesting, for sure, but ZFC does not need to be the standard in order to do that. Surely the purpose of a standard is to provide a firm philosophical foundation, right? And so it should be justified on philosophical grounds, not, well, that's what we've always done and it's worked so far, which is perhaps a slightly unfair characterization of the general position, but only slightly. Oh well. All anyone can do, I guess, is decide for themselves what they believe in. And personally, I think it's time to wake up from ZFC. If you're interested in a metaphorical pinch, I recommend reading up on the continuum hypothesis, as well as all the further reading in the description.